In this video, we will attempt to prove the Kuratowski's theorem. In this case, it's going to be a sketch of a proof rather than full rigor, because we're talking about drawing and we're not going to get into the topology to make everything fully rigorous. So the idea is to prove our result by induction on the number of vertices plus the number of edges. So the claim was that G is planar if and only if it does not contain a Kuratowski subgraph as a topological minor. As already discussed previously, if G is planar, every topological minor of G is planar as well. So if G is planar, it cannot contain K33 or K5 as a topological minor. So we're going to go the other direction. Suppose G is not planar, then what we're going to prove is that you can find a Kuratowski subgraph inside of G. The whole point then is that in any attempt to draw G, you look at that Kuratowski subgraph and you will find a crossing as a result. All right, so this is going to go in cases. First, suppose your graph is disconnected. Well, if every component of your graph was planar, then just draw each of them in different regions of the plane, and you have a planar drawing of G. So if G is disconnected, there has to be some component of G that's not planar, and so by induction, that component has to have a Kuratowski subgraph. So thus we can assume that our graph is at least connected. So now we're assuming our graph is connected. Let's show that we can reduce to the case of being two connected. So suppose your graph has a cut vertex. Then when you delete that cut vertex, you're going to get a bunch of different components. If all of those components are planar, then you can draw them in different regions. And remember before we said that you can draw with your favorite vertex on the outer face. So draw each of these components with V on the outer face and then just glue the drawings together. And the result should be planar. So this tells us that some component of G minus V is not planar. And hence by induction has a Kuratowski subgraph. So thus we can assume that our graph does not have any cut vertices. So now let's assume that we have a separating set of size 2. Suppose there are two vertices x and y, such that G minus xy is disconnected. Then what we're going to do is take each component of this deletion and add in the edge between x and y. If each of these components is planar with these added edges, then so is the original graph. And the idea is in each of these components, well, you use induction, G minus C is planar. Now draw a plane graph of this MC with that edge on the outer face, and then glue these two drawings together. So again, our theory about being able to draw nice subgraphs in a nice way with your favorite vertex or edge on the outer face is really doing some heavy lifting here. All right, so we can assume that there exists some component of G minus xy, such that when you add in the edge xy, you get something non-planar. By induction, this subgraph has a Kuratowski subgraph H. And if that Kuratowski subgraph H does not use the edge xy, then it is in fact a Kuratowski subgraph of G. So now we're in the case where we have to concern ourselves with what happens when our Kuratowski subgraph uses this new edge, which might not have been our original graph. Then we got this nice little trick we can use, which is that there was another component of G minus xy, and each x has to have a neighbor in that component and y has to have a neighbor in that component, because otherwise there's a smaller separating set. And so this means that we've got two vertices in this other component, one adjacent to x, one adjacent to y. Because this other component is connected, there has to be a path between them. And now I have this blue path between x and y that doesn't involve any of the vertices in MC. So the point is, if I replace this red edge with this subdivision multiple times, I get this blue path. And so I'm guaranteed to find that G does in fact have a Kuratowski subgraph by just subdividing the edge xy several times. So this ends the case of what happens when your graph has a cut vertex or a separating set of size 2. So now finally we are in the case of what happens when G is 3 connected. If it's 3 connected, it has at least 4 vertices. When it has 4 vertices, then the only option is K4, which is planar. So we're looking at a non-planar 3 connected graph. It must have at least 5 vertices. Based on what we've studied about 3 connected graphs before, this means there exists an edge in our graph such that when we contract it, we still get a 3 connected graph. So now we have 2 cases to consider, either the case where the contracted graph is not planar or the case where it is planar. So first, suppose it's not planar. By induction, it must have a Kuratowski subgraph H. The goal is to somehow create a Kuratowski subgraph in G using H. And there are obvious cases to deal with first. If our contracted vertex is not in this Kuratowski subgraph at all, then it is already a Kuratowski subgraph of G, because every vertex and edge in H is already in G. So now we need to look at the case where the contracted vertex is a vertex in our Kuratowski subgraph. Then there are some cases we have to consider. The first case we can consider is looking at the possibility of replacing VE with X or Y and still getting a Kuratowski subgraph in G. So this is going to happen if the neighborhood of our contracted vertex is contained in the neighborhoods of one of our 2 endpoints. If that happens, then the whole point is you took a Kuratowski subgraph with a vertex labeled VE, you just relabel it with X or Y, and you actually have a Kuratowski subgraph inside your original graph G. So in other words, what's going on is you've got this setup, you've got this edge we've contracted, all the neighbors of the contracted vertex are contained in the neighbors of X here. We're assuming that we have managed to create a Kuratowski subgraph H that involves this contracted vertex. The point is that the other endpoint along these edges has to be over here, and so if I just replace VE with X, I get a Kuratowski subgraph in G. All right, so the interesting case is when this doesn't happen. And then this also breaks up into subcases. First, if the contracted vertex is degree exactly 2, then the point is both of the endpoints of VE have to lie in our Kuratowski subgraph. The point is take one of those edges incident to VE and subdivide it and label it the resulting vertices as X and Y. And congratulations, we took a Kuratowski subgraph of our contracted graph and replaced it with the Kuratowski subgraph in our original graph. So this means we need to be looking at the case where the vertex VE has degree higher than 2 in our Kuratowski subgraph. And this is the final case where we start to actually have to look at H and whether it's a subdivision of K33 or K5. So first, suppose H is a subdivision of K33. Remember, our contracted vertex is degree greater than 2 in our contracted graph in this Kuratowski subgraph. And so that means it must be one of these 6 vertices. And so suppose it's this one right here, highlighted. There's its 3 neighbors. The whole point is take any one of those 3 edges and subdivide it and replace it with X and Y. And then we're good to go. There is a slight gap here I have to point out. This is assuming that Y is adjacent to one of these 3 vertices. But if it was not, then it would follow that the neighborhood of VE is contained in the neighborhood of X, and we'd fall into a previous case we've already discussed. The other case is what happens when H is a subdivision of K5. Then again, your contracted vertex has to be one of these 5 vertices. It has degree 4. Then I tried to draw the 2 cases we have to worry about. So these depend on the neighborhoods of X and Y. If X and Y are both adjacent to 2 of these different paths, so that if you're pretending this is a graph, you could pretend X is adjacent to 2 of these vertices and Y is adjacent to the 2 others. Then the picture you draw is this one, where you replace this vertex with X, Y, and draw the corresponding paths. And then, based on the coloring, there is a topological minor of K33. So the only other case would be if x or y, without loss of generality, let's assume x has only got a path to one of these four vertices, then this is the picture you draw. You take this last path here and subdivide, and now you have this situation, which is a K5. So at this point, you're starting to see why we call this a proof sketch, because verifying all these details gets quite technical. So the proof of Kuratowski's theorem is actually quite involved, particularly since at this point, all we've done is assume there exists a Kuratowski subgraph and then find a way to make it bigger, which leads you to wondering if it's ever possible to find a Kuratowski subgraph to begin with. And so that actually results in our very last case. So here we are assuming G is 3 connected. We're assuming that we've contracted it, G by an edge, and gotten a 3 connected graph. And we're in the last case where we're assuming that this contracted graph has a plane drawing. And what we want to prove is that our original graph has a Kuratowski subgraph because it's not planar. So what are we going to do? Well, if I take my contracted graph and I remove the contracted vertex, I have to get something 2 connected. Let's take a plane drawing of G contracted E minus VE, and let's look at the face that contains VE in its interior. Because this graph is 2 connected, the boundary of my face is a cycle. Moreover, the neighborhood of my vertex X is contained in the neighborhood of this contracted vertex. It's contained in the cycle. So the point is we're going to be looking at the neighbors of X and Y along this cycle. So let's label the neighbors of X along the cycle clockwise as X1, X2 up to XK. So somewhere out here we have X1, X2, and so on. So then what are we going to do? Now we're going to look at the neighbors of Y. Suppose there are 2 consecutive neighbors of X along the cycle with the property that the neighborhood of Y is contained entirely in this arc. Then what I could do is replace the contracted vertex with X, draw an edge to Y, and connect Y to these neighbors. And I see as a result G is actually planar. This gives me a plane drawing of G, which is a contradiction because we're assuming G was not planar. And so that tells me that Y must have neighbors outside this segment for any pair of consecutive neighbors of X. So one example we could end up with is it might be possible that Y has 3 neighbors in common with X, like this way. Then what happens there? Well, I look at this edge between X, Y, I look at these 3 vertices. Notice that because there's this outer cycle, I have these paths between Xi, Xj, and Xk. And so with all 5 of these vertices together in these paths, I see that I have a subdivision of K5. So what other case could there be? Well, if we're not in case 2, then Y can only have neighbors with at most 2 common neighbors with X. But we're not in case 1, so this means that Y must have neighbors on 2 different segments of the cycle. So that means there has to be X has to have neighbors Xi and Xj, where Y has a neighbor between Xi and J on this side and between Xj and Xi on that side. Suppose this is true, then again look at these 6 vertices, look at the drawing, I see K33. And so in the worst case scenario, if your graph is not planar, but you found and it's 3 connected, and you found an edge such that the contracted drawing was planar, then you could use that plane drawing to construct your Kuratowski subgraph. And then all the other cases involve finding Kuratowski subgraphs in a component and somehow redrawing it so it's a Kuratowski subgraph in your original graph. And this ends the proof of Kuratowski's theorem.